In this lecture, we will be studying the concept of the improper integral. If we think back to our study of integral calculus, one of the concepts we focus on is often called the area problem. So if we're looking on an interval, AB, and we have some function that's non-negative, and we want to consider the area below the curve over the interval AB. And we learn that this, defined as the definite integral from a to b of f of x dx, as a limit of Riemann sums, gives us this exact area. We're going to modify this scenario a bit. In particular, we're going to change these endpoints to be infinite. So an improper integral, often called the first type of improper integral, we now have a function that's defined on a infinity, greater than or equal to 0. You don't necessarily need that, but it makes things a little bit nicer. And we now want to define the integral from a to infinity of f of x dx. So now if we're here at a, and our function looks something like this, we now want to know what's that area below the curve, below the graph of the curve y equals f of x over the infinitely wide interval a to infinity. And how do we define this? Now the key question will be, is this area finite or is it infinite? And the way that we will answer that question will depend on this function f. And this is essentially a race to 0 for this function f. So the question will be, does f of x decay to 0 fast enough as x goes to infinity for that area to be finite? So again, let's draw our curve. Number one, it's necessary for this graph to race to 0. If it doesn't, imagine a situation where the graph looks something like this. Say it was constant. Well, I think we can all see intuitively that the area below the curve, say y equals 1, from a to infinity would be infinite. So we need the function to approach 0. But approaching 0 is not enough. It has to approach 0 at a fast enough rate for that area below the curve to be finite. Well, looking at this problem, we may say, how do we make sense of this? The integral from a to infinity of f of x dx. Usually for the definite integral, our approach is to partition the interval and let the norm of the partition go to 0. We could do that. It feels a little bit complicated here to do that. But we can actually take an approach where we break this up into 2 steps. Essentially, a differential calculus step and an integral calculus step. So let's do the following. Instead of integrating, instead of getting the area all the way down the real line, let's stop. Let's stop at, say, some arbitrary value t and calculate this area. Now, if we calculate this depicted area here, that is nothing more than the integral from a to t of f of x dx, and that is our usual type of definite integral that we learned when we studied integral calculus. Once you have that area, you now will have that area dependent on t. The second step, we can use what we learned in differential calculus and send t to infinity. Of that, you can think of it as this depicted area. Now, as t goes to infinity, this shaded region fills in all of the area below the curve, and when you take that limit, you get the actual exact value for the area below the curve. And that gives us our definition of the definite integral from a to infinity of f of x dx for such a function, non-negative on a infinity. So you see we've broken it up into those two pieces. So this first piece is a regular old definite integral, which we already know how to do. And then once we have that expression, right, it will be a function of t. We then let t go to infinity. And this approach will always work. This is how you approach the calculations of definite integrals. And note that you can go the other way as well. We can also have the integral from, say, minus infinity to a number a, or why don't we say to b, of f of x dx. And you define this in a similar way. Here you would say the limit as t goes to negative infinity of the integral from t to b of f of x dx. And we will look at in the next lecture how you do calculations with these. But it can also be helpful to know, why is this important? This comes up in calculus in many different settings. One example, one setting where it comes up a lot, is in probability theory and statistics. This function is what we, at this point in our math studies, may have heard of as the bell curve. Put another way, this is the density function of the standard normal distribution. And if you graph this function, it looks something like this. And there are many, many calculations that are done where you are integrating this function, actually not only from having an infinite limit on one end, but on the other. In fact, in this case, if you do this integral, because it's what we call a density, you get 1. Now, doing this integral is not easy. You actually can't find an antiderivative to this. You have to get a little bit creative, and it's something that we would study later in calculus. So we're not actually going to do this improper integral. We don't have the tools for it yet. But it's important to recognize that most of us have heard of the bell curve. And integrals, improper integrals of the bell curve, functions times the bell curve, are extremely common. So you see things like this will have another function times that bell curve function. And these types of calculations come up in probability theory and statistics all the time. And so this kind of illustrates pretty well through a standard example how the idea of the improper integral, the tool of the improper integral, comes up all over the place in mathematics.